In this lecture, let us discuss about measurement error and uncertainty. When you are performing experiments in wind tunnels, in all such experimental measurements, there would be some kind of error. By definition, an error in a measurement is the difference between the exact value and the experimentally recorded value, which will be your measurement. It is of course a fixed number for a certain measurement that you perform, and therefore, it is not statistical in nature. Coming to uncertainty, uncertainty is a probable value that the error might take in a given measurement. So, it is not a specific measure, it is only a probable measure. Because the uncertainty can take on various values over a certain range, it is essentially a statistical variable. So, this is the underlying difference between error and uncertainty. A measured value describes the central tendency or mean of the recorded parameter. So, if you take a number of measurements, you will find that all of them tend to be falling this way or that way of a certain average value. That means, it shows the mean, the tendency of the average, while uncertainty describes the dispersion of the recorded parameter. That means, over what range it may be varying, what kind of error range may be involved. That means, often you would look for measures like standard deviation for representing uncertainty instead of mean. Let us discuss a little bit more on measurement errors. In an experiment, the value of the measured quantity is x m, let us suppose. The correct value of the parameter is x c, and we may be able to independently estimate the correct value by some means. It could be from theory, it could be from available high accuracy computational result, or available high accuracy experiments which have already been performed. That means, there is some basis on which we may be independently able to estimate the correct value as well. Now, due to measurement uncertainty, the measured quantity is not equal to the correct value. So, x m is certainly not the correct value, there is certain difference between x m and x c. Now, this difference is of course the error, and that is equal to the difference between the correct and measured quantities, which we already mentioned, x c minus x m, c for correct, m for measured. The error can be either positive or negative. That means, we may need to add it or subtract it from the measured value to reach the correct value. Again, the measure of the error could be also in a fractional sense, where instead of representing it as e, we may represent it as epsilon, where we normalize that e with respect to the correct value. To utilize the measurement meaningfully, it is essential that we have some estimate of the error either in the form of e or epsilon. From the above equation, that means this equation, it is evident that if nothing is known about the error, then the measurement x m tells nothing about the correct quantity x c. That means, as long as you have some estimate of how erroneous your reading has been, only then you know that whether you are anywhere close to the correct result or not. That assessment is absolutely essential. Now, the errors that are likely to be associated with the measured quantity x m are the external estimate epsilon e and the internal estimate epsilon I. Let us try to elaborate. Epsilon E is based on the knowledge of experimental work carried out by others, which may be already done, completed. And through those experimental works, it may have been established already that xm is basically a function of 4 variables, let us say A, B, C and D. And of course, errors were involved in measuring those 4 different variables as the experiment was conducted, and those errors in the epsilon sense could be epsilon subscript A, B, C, D respectively, due to independent sources. That means one does not influence the other. In such a situation, the external error in absolute terms can be expressed like this without going into much derivation of how we arrive at this result. This is a standard result which we are trying to cite here directly. So, the square of the effective error or the resultant error in absolute terms, which is defined by small e suffix capital E, which is the external estimate in absolute terms, is a summation of the partial derivatives of the function f with respect to the corresponding variable squared and then multiplied with the error associated with that variable. That means, it will go as del f del a square E a squared E c squared and E d squared. And then if you try to convert it into a relative or fractional sense, then you can establish this relation. So, this is essentially the effective or resultant error. There should not be a square here, it should be just epsilon suffix capital E. So, that is a mistake, please take care of that. The internal estimate epsilon I is assessed based on the data obtained during the present experiment. When carrying out the experiment, it is advisable not to rely on a single measurement of a quantity. It is a matter of common experience that these repeat measurements will not give identical values of the quantity which is being measured. So, every time you measure, you get a slight change in the value. So, you record them by repeating the results and watching out how repeatable the results have been. They should show you a trend, but then they should also show you some dispersion, and that essentially would give you some assessment of the errors and subsequently even help you assess the uncertainty, which we will discuss about later. So, the variation among the measurements will help you to assess the epsilon I. Now, when the two estimates, which is nothing but epsilon capital E and epsilon capital I, are fairly close to each other, the experiment may be treated as a reliable one. That means, essentially the present experiment will then be treated as a reliable experiment. A little more on different types of errors. Independence and dependence of errors. So, in the estimation of the external error, the different error components involved in the measurement were considered to be independent, which we mentioned in the previous slide. So, for example, if epsilon A is negative, it cannot influence the sign of epsilon B, C, D, neither the quantities. This situation is called as independence of errors. That means, each error component varies independently and is not influenced by the others, neither does it influence the others. However, that may not always be true. There could be dependencies between different kinds of errors. One may influence the other. There could be a kind of cascading of errors. And therefore, when dependencies occur between error components, we say that there is a situation existing which leads to dependence of errors on each other. So, we have therefore either independence or dependence of errors. Again, you can classify experimental errors through another means, that is whether it is a fixed or systematic error, or it is a random error or non-repeatable error. So, for the case of fixed or systematic error, what happens is repeated measurements contain the same amount of error in every reading. There seems to be a kind of offset in every reading. This error is the same for each reading and therefore can be removed by proper calibration and correction, because it is repeating systematically. However, if errors are random or non-repetitive, the error quantity would vary from one reading to the other, and hence they cannot be removed from the measurement because they are inherently random in nature. They are inherently statistical in nature. So, we learned a bit about different kinds of errors. Now, let us discuss about uncertainty, and to begin with, let us discuss about some of the utilities of uncertainty analysis. So, what does uncertainty analysis try to achieve for us? It examines the overall accuracy of the experimental procedure, and it helps identify the potential sources of error and the dominating sources of error. So, dominating sources of error, that will make it more specific. So, potential and dominant sources of error. Also, the overall accuracy. So, you would certainly say that an experiment is a very reliable one where the uncertainty is on the lower side, on a very narrow or small side. It helps identify the instrument or procedure that virtually controls the overall accuracy. So, there may be number of instruments or number of procedures which may be involved in an experiment. So, when you perform an uncertainty analysis of the entire setup comprising of all the instruments in the chain, all the procedures involved in the measurement, then you get a very clear idea that which particular instrument in the chain or which particular procedure in the measurement is actually controlling the overall accuracy. The one which is contributing to the error on the higher side is certainly going to be the dominant factor in the uncertainty which is created in the result. So, one that controls the overall accuracy, the identification of the same is very, very important, and that can be achieved through uncertainty analysis. It helps to decide better whether the instruments that you are using or the experimental procedure that you are using, they need to be improved, whether you need to use better instruments or better experimental procedures for conducting the experiments, so that you are able to achieve desired output accuracy. So, with the existing instruments or procedure, if you are not reaching what is intended, then you need to do betterment, but then randomly changing all the instruments or all the procedures in the entire experimental setup won't help. So, if you can pinpoint that which instrument or which procedure needs to be changed, so that you can improve the overall accuracy and reach the desired level, then that is the most appropriate way of going about it, which uncertainty analysis will achieve for you. The identification will be done by uncertainty analysis for you. It helps minimize instrument cost for a given output accuracy. So, it may be that you could achieve a desired output accuracy with a very cheap instrument, while you are actually investing a lot to buy a very costly instrument just to do a little bit better. Therefore, you can cut down on your instrument cost significantly if such assessment is made. It could also assist design of instruments to a better level to ensure minimum uncertainty. That means, you could improve the designs that you are using for the instruments that you are using, so that your uncertainty can be minimized. So, there are so many utilities which are associated with this analysis, and therefore, it is worth having a look at it. Let us look at the general procedure for uncertainty quantification or estimation. So, let us suppose that in a given situation, in a given experiment, you have a number of independent variables. Here we are mentioning them as x1, x2 up to xn, which are the independent variables in an experiment, and let us say u1, u2, un are the relative uncertainties, like we talked about relative errors earlier, and let ER be the experimental result calculated from the above measurement. So, the experimental result is a function of x1, x2 up to xn. Now, if there is a small variation, say delta xi in the ith measured variable, then its influence on ER will be given by a relation like this. So, delta ERI, that means the small change, a small variation in the experimental result due to change in the ith measured variable is delta ER suffix I. How do you calculate that? You take a partial derivative of the experimental result with respect to that particular ith variable, that is del ER del xi, and then you multiply it with the small variation delta xi of the ith measured variable. So, that is how you try to evaluate the change in the final experimental result based on that small variation delta xi. Now, you could normalize this expression by dividing throughout by r, rather ER. So, what does that produce? It produces a ratio delta ERI by ER on the left hand side, and then on the right hand side you have a 1 by ER multiplied with the previous right hand side, and now we rewrite it slightly by introducing xi in the numerator, and that is balanced by a xi here in the denominator. Finally, with this form, what do we move on to? We move on to a form where uncertainties can be introduced. So, if you look at a ratio like this, the variation in the ith measured variable divided by the original value of the ith measured variable, that gives you the uncertainty, and then xi by ER is a certain ratio, del ER del xi is a certain derivative which is multiplied with this uncertainty. On the left hand side, you have the variation in the experimental result by the original experimental result, which is there without a variation, which is again the uncertainty in the experimental result due to the ith component. So, now you have a relation which connects the uncertainty in the ith component with the uncertainty which it produces in the final result. The combined effect of uncertainties in this way, which is accounted by the following equation, comes from the contributions of the other components. So, like we did it for uxi, you can apply it now for I equal to 1 to n. So, it starts with ux1, moves on to ux2, uxn. So, you square all the contributions, sum them up, take a square root, and a plus or minus value of the square root basically gives you the uncertainty of the experimental result. So, this is basically the framework. Now, let us move on to do a brief calculation for a particular practical situation in order to get a better feel of what we are talking about. So, let us say we are trying to measure the pressure distribution on a body, let us say an airfoil, where the flow has gone through an adverse pressure gradient, and maybe you are measuring the pressure at a port where it is already into the separated flow. So, the pressure is fluctuating quite a bit because of the flow separation, and you are trying to identify that as a result what would be the impact on the uncertainty. When you have a very stable steady pressure, obviously the uncertainty is expected to be on the lower side, because there would be no fluctuations in the measurements. But when there are fluctuations in the measurements, the uncertainty is expected to be high. So, here you are essentially setting out to work out Cp, which we are defining it as P minus P infinity by P naught minus P infinity, the numerator indicated as P1, denominator indicated as P2, which are going to be measured using suitable instrumentation. Let us say in our case it is manometers. So, in order to perform the calculation, we first write an expression like this. And then you know that del Cp by del P1 would be 1 by P2 using this functional expression. Del Cp by del P2 will be minus P1 by P2 square. You need them here in these expressions. Therefore, you get 1 by P2 dP1 minus P1 by P2 square dP2. Now, when you come to UCP, you are trying to find out the uncertainty in Cp. What you need to do is P1 by Cp del Cp del P1 UP1 square plus P2 by Cp del Cp del P2 UP2. That is following the relation that we discussed in the previous slide. So, this is what you are going to evaluate. So, of course, UP1 and UP2, they are the relative uncertainties for P1 and P2. So, this would be defined as say delta P1 by P1, this would be defined as delta P2 by P2. Now, if we move on, let us say that the nominal free stream velocity in this case is of the order of 30 meters per second, and the pressure that has been measured, the P1 nominal value is of the order of minus 783 pascals, P2 is of the order of 540 pascals. The nominal value of the Cp is of the order of minus 1.45, and if you look at the measurements that you did using your manometers, you saw some fluctuations, and by repeated observations it was estimated that the maximum possible errors in measurement of P1 is of the order of 2.5 millimeter water column, and P2 is 0.5 millimeter water column. That means, about the mean value, the P1 and P2 measurements fluctuate by those quantities. The fluctuation is more here because there is unsteady behavior of the flow field due to flow separation. Now, if you perform the calculations, then you will find that the first expression P1 by Cp del Cp del P1 UP1 can be given by minus 783 by 145 into 1 by 540 into, we have not assessed UP1 yet. how do we do it? So, u p1 would be of the order of plus or minus 2.5 by 80. Now, this 80 millimeter is the delta H for the P1 case. So, delta H1 is 80, that is the difference between the two limb levels, and therefore, this ratio will come to 0.03125. So, incidentally, when you perform this calculation, that will also give you the same, because the other numbers get cancelled, and if you perform the calculation for so this is UP1 for the second component, it will turn out to be into now you have to estimate UP2. UP2 is plus or minus 0.5 by 55 millimeters. So, that is coming from delta H2 corresponding to that pressure that we have already mentioned. So, that gives you an estimate of plus or minus 0.009. Now, incidentally, this will ultimately end up giving you the same number. Finally, the UCP calculation will come out to be plus or minus 0.03125 square plus 0.009 square raised to the power of half, which is 0.0325, which is 3.5%. And you know now that bulk of this uncertainty is coming from the measurement of P1. The P2 part has trivially contributed to this error. So, in this lecture we discussed briefly about measurement error and uncertainty. It emphasized the fact that aerodynamic experiments yield data which can be meaningfully utilized only if we have a reasonable estimate of the error and uncertainty accompanying the data. Without that knowledge, we cannot make useful implementation of experimental data. Thank you.